Okay, so we covered this question here about a water wave that's traveling at a certain speed and has a wavelength, and we can figure out its frequency. The way that we solve this is by dividing the velocity by the wavelength, and we get the frequency. So we're just applying that equation. And what would be two different ways that we could find a speed of 100 meters per second? So in other words, like, basically, you can pick any frequency and then just pick a different wavelength in such a way that they equal to 100 meters per second. So for example, if I gave you a frequency of 2.5 hertz, we could actually figure out what to multiply that by to get 100. So for example, going back here to this if we had a frequency of 2.5 hertz, and I wanted to figure out what wavelength to get a velocity of 100 meters per second, I could just take lambda is equal to v over f and say that's 100 divided by 2.5, and I cannot think of how to do that in my head at the moment, so I'll just do 100 divided by 2.5, and that's 40. Good. So that is going to be 40 meters. So in other words, if I plugged in f times lambda, that's always going to be my speed. And if I plugged in a f of 2.5 hertz and a lambda of 40 meters, if I multiplied those two together, remember this is per second, so meters per second, 40 times 2.5 is 100 meters per second. Another thing that I could do, for example, is if I had a frequency of 5 hertz, then that one's a little easier. If I wanted a velocity of 100 meters per second, I can do 100 divided by 5, which is 20, and so lambda is v over f. It's going to be 100 divided by 5, or 20, and that is going to be 20 meters. So in other words, if I used a lambda of 20 meters times f, that could be my speed, and I could say this is going to be 20 meters times 5 hertz, or cycles per second, and that will give me 100 meters per second. So you see that there's a variety of things you can do. You can always, for any wavelength, you could, if you change if you had a wavelength and you have a different frequency, you can figure out that right combination to get the speed you want. Now the catch is that in sound has a fixed sound has a fixed velocity. That's the catch. And so you don't get to just choose your wavelength and your frequency in such a way to get the speed that you want. You're basically fixed with this speed. So in other words, if the wavelength becomes larger, the frequency is lower. If the wavelength becomes shorter, the frequency is higher. And so you have that kind of relationship with sound, and that's an important part of our puzzle piece as we're trying to sort through how to understand sound waves. Okay. So there's many correct answers to doing this. The ones that they offer here in the slides are 25 hertz and 4 meters. Of course, 25 times 4 is 100. Okay, let's take a look at another example. A sound wave has a speed of 343. Okay, this thing they say 343. We usually say 344, but that's okay. 343 meters per second in the air. What is the wavelength of a sound wave with a frequency of 686 hertz? So here we have the equation v equals to f times lambda. We have v is 343, we have f is 686, and we have to figure out what lambda is. How do we do this? I want you to pause, calculate it, figure it out, get a number. Okay, we're back. Hopefully you figured out that if we have a speed that's 343 meters per second and a frequency which is 686 inverse seconds, or 1 over seconds, and we need to figure out lambda. Lambda is v over f according to our formula. And so here, 343 meters per second divided by 686 inverse seconds, seconds cancel out, and we're left with 343 divided by 686. Now, if you have some experience with this, you might say, oh, wait a second, 343 is just half of 686. But if you're not sure, it's also okay to simply use a calculator. I like to just use this Google calculator because it's easy. We can type in 343 divided by 686, and we see that it's 0.5, or 1/2. So we can write that this is equal to 1/2 of a meter. So our wavelength is 1/2 of a meter. Now we'll go back to the slides. Okay. So the way that we solve this is we say that it's 1/2 a meter, which is also the same thing as 50 centimeters. So what happens if the frequency is doubled? Well, you can try this in the simulation. You can make, and the catch is really this, is that this question here is vague because are we assuming that the speed is the same? For sound, that's the case. But you could also imagine a situation where maybe the wavelength stays the same, but the speed is what changes. So in the case for sound, we're going to usually assume that the speed of the wave remains fixed, just because we know that all sounds travel at the all frequencies of sound travel at the same speed. So if the frequency doubles, then if the speed stays constant, that means that the wavelength becomes half as much. If you increase the volume, that means how loud it is. What wavelength is, or what characteristic is affected? It's the amplitude. In other words, we go to higher pressure and lower pressure. So to refer to page 27 of your book, you can see here that this page shows the amplitude of the wave as just being 0.1 pascals up, 0.1 pascals down. So if you increase the volume, this would become maybe up to 0.2 up, and then down to the 0.8 down here. So you might be 0.2 up, 0.2 down. Or you have a really high amplitude wave that's going to be even louder. Okay, so that's the concept there for how to figure out how volume or loudness is related to the characteristics of the wave. All right, so now it's time to test our knowledge. So hopefully you've been able to put together some of the ideas that we've been discussing so far. One is that the height of a wave versus time is shown, and then the height of a wave versus distance is shown. So I want you to get familiar with these concepts that a wave that's propagating, I could do it both as a snapshot, where I am actually like taking a picture of this wave. Imagine there's a bunch of ripples traveling across the water, and I took a snapshot with a photo, right? Then that would give me this picture, height versus distance. Whereas if I recorded a rubber ducky going up and down in time, that would give me this one here. Based on these two graphs together, we can figure out everything that we need to know about the wave. So let's work through it together. What is the wave frequency? Well, in order to do this, I need to refer to the time graph, because I know that frequency has to do with time stuff. And I can see here that every second, this thing seems to repeat itself. If you're not exactly sure, you could always count and say, I have 1, 2, 3, 4, 5 in 5 seconds. So in other words, there's 5 cycles, 5 seconds to do 5 cycles. So that means that there's either, you can think that there's 1 oscillation per second, or it takes 1 second to do an oscillation. In either case, you'll see that the wave frequency is 1 hertz. The wavelength, this is a length, so we need to go to the height versus distance graph. So here I can see that, for example, between this peak, which looks to be at about 2.5, so that looks like these units are the way that these markings are. It's a little bit strange because you have 1, 2, 3, 4 to get to the 5 one, right? So, but nonetheless, you can see that. Let's take where it is at 5 and go up to 10. That's a place where it's repeating itself. So it looks like every 5 centimeters. And careful, we got to check those units. Every 5 centimeters, this thing repeats itself. So I would say that the wavelength would be 5 centimeters here. What's the amplitude of this? Well, this is how much the wave, if it's like a physical water wave or something, it goes up by 10 centimeters and down by 10 centimeters. Notice how this height is going to be the same, no matter whether you're looking at it in time, in other words, a rubber ducky going up and down, or if you took a snapshot of the water, that it would be the same height going up and down, okay? And so that is 10 centimeters above, 10 centimeters below, so that means that the amplitude is 10 centimeters. Finally, we have one more challenge, which is to calculate the speed of the wave. Well, this is the most challenging part, actually, but if you remember our formula for speed, you can realize that since we already figured out the frequency, we already figured out the wavelength, now we can just simply calculate the speed. So I'm going to go back to the camera for this one, and let's say that we figured out now that the frequency is equal to 1 hertz. That rubber ducky's going up and down 1 time per second. The wavelength we figured out is 5 centimeters. That's 0.05 meters or 5 centimeters, right? That's the same thing. And we know our formula that V is equal to F times lambda, or lambda times F. And we see that it's going to be 1 over seconds, times 0.05 meters. If I multiply those units together, I'm going to get meters per second. Oh, good. That's a good check to make sure that I've done it correctly. And then 1 times 0.05 is just 0.05, but now my units is meters per second. So, in other words, what I've got here is 0.05 meters per second or 5 centimeters per second. Either of those are correct. So this is a really key point here is how we calculate the speed of the wave. You basically just figure out the wavelength, figure out the frequency, and now you can know the speed. And so here are the answers, just as we had discussed. You can pause it if you need to look at those or check the slides. Okay, so let's try another question here. So 2 students use a 10-meter long spring to create a standing wave. The wavelength that they create is 2 meters, and the frequency is 2 hertz. So basically, maybe it's a transverse wave, maybe it's a longitudinal wave. Doesn't matter actually in this case, but it's just like the demos that we've done. How fast is the wave traveling along the spring? We're asking for a speed v, and so we're given that it's 2 meters is the wavelength, and the frequency is 2 hertz. And so the relationship here is that v is equal to f times lambda. We plug it in, we get the answer. It's pretty straightforward. But nonetheless, I think we should also solve this problem with you doing a little bit of a visual. So in other words, this can be a little bit difficult to do because, I mean, to draw a picture, but if you imagine that this one student here is holding on to the spring, and the other student maybe is holding on over here, and they wiggle it like this, and there's something moving, right? Then you can take a snapshot, figure out what the lambda is. That's going to be our 2 meters in this case. And we can also say that if we were to watch these waves going by, we'd say that there was 2 going by per second. So the frequency is going to be 2 hertz. And so again, this is a straightforward problem where we really can just skip right to the formula and say v is equal to f times lambda, which is going to be 2 times 2, or in other words, 4 meters per second. Okay. Move on from that example here. So waves carry energy from one place to another. You can also think of it as they carry information. Is another way to think about it as well. Waves propagate through space and they spread out their energy into other regions that could be far away. So some interesting examples of waves are, for example, the cosmic microwave background radiation. This is light that began from the early origin of the universe 13 billion years ago, which is just getting to us now, and it's telling us information about the early origin of the universe, which is some really interesting stuff. If you wanted to make a cell phone call, you've actually got to send radio waves out to a cell tower, which then retransmits that radio wave to another person. So as a wave moves through matter, its energy causes the matter to respond. After the wave passes, the matter returns to equilibrium. So you can imagine like this droplet and the waves expanding, and if you were a rubber ducky here, at first you would bob up and down a lot, and then after a while you would settle down. So this kind of would go up and down and up and down, and then eventually would kind of peter out, and that's normal. And this has to do with the dissipation of a wave. Same thing if you hit a drum. You would hear a sound for a while, and then that energy would dissipate. The energy of a wave increases with frequency. So actually the faster oscillations, you can imagine the rubber ducky going up and down really fast is going to have a higher energy than one that's moving up and down at a lower frequency. Also, there's more energy in a wave if it has a larger amplitude. In our sound case, this will correspond to a higher volume. This will correspond to a lower volume. So as a wave spreads out in space, its amplitude decreases. One reason for this is that there's damping, so there's friction causing the wave's energy to reduce over time. And so, for example, like the water droplets, like the molecules of water inside of this thing, inside of this like a bowl here, they're going to be moving and rubbing up against each other and creating some heat. Another reason is that as the wave propagates outward, it has to spread its energy over a larger space. So that's why, for example, like if a bomb were to go off, the farther away from the bomb you are, the more safe you are. Okay, so here's an interesting idea. As you get farther and farther away from the source of somebody talking, it may get quieter, but the words and the tones stay the same. Why is that? Well, the amplitude of the wave is going to be reduced, but the frequency still remains the same. So the actual like information content is actually going to be exactly the same, but it will just be the amplitude, which you can see here, is going to become less and less. In 3D, we can think about the waves moving forward. I'm going to just skip through this right now. Transverse waves, of course, we've talked about. Examples are waves on a string. Light waves also are a kind of transverse wave because the electric field is pointed up and down while the wave moves from left to right. And we'll talk more about that in the future. Just to remind you that transverse waves, we did an animation like this before, and you got to see the different ways that they either vertical or horizontal motion, but yet the wave moves from left to right. And a longitudinal wave, for example, is a sound wave, or the waves in a spring as shown here. If you move this back and forth, you create a compression wave which moves through. So our longitudinal waves, we write here as the density. So it's higher density here, it's lower density here, higher density here. And you can see that this graph here is actually corresponding to this compression wave. Polarization, as I mentioned, is just going to be briefly talked about here, is that this has to do only with transverse waves, and has to do with whether the motion is up-down as the wave moves forward, or if it's from side to side as the wave moves forward. So this is the kind of idea about polarization. Longitudinal waves, such as sound waves, cannot be polarized. Okay, so this was our assessment. We already figured this thing out. Oh, we did not. This is basically the problem that we had solved before. I want you to pause and take a moment to see if you can answer this question. I guarantee you there will be a few questions that are kind of like this on our future exams. So please take the time to try and solve these 4 questions here in this assessment. Okay, and we are back. So the frequency, as we can figure out here, has to do with how many time cycles are there per second. Well, I could go through here and say from 0 to 2 is 1 cycle. From 2 to 4 is another cycle. So that means that the period is 2, or in other words, 2 seconds, or the frequency is 1/2 of a hertz. The wavelength, I have to go to the distance graph now. I can see that from 0 to 20 centimeters, that's the distance over which this waveform repeats itself. So that must mean that the wavelength is 20 centimeters. So the amplitude, as you can see, it's the same on both. It's going from 0 to 0.5, 0 to 0.5. And so that amplitude of the wave is going to be 0.5 centimeters. Finally, we get to calculate the speed of the wave. And in order to do that, I'm going to go back to the camera here and get a new fresh piece of paper. We found that write down the numbers here. We found the frequency was 1/2 of a hertz, and the wavelength we found to be 0.2 meters or 20 centimeters. And when we do that, we need to figure out the speed. Speed is frequency times wavelength, or in other words, 1/2 times 0.2, and again, I'll keep these units 1 over seconds, meters, and 0.2 divided by 2 meters per second is going to be 0.1 meters per second. Okay? That's going to be our speed of the wave. And let's see how we did. 0.5 hertz, or 1/2 of a hertz, 20 centimeters, 0.5, and we just put in 0.5 hertz, 0.2 meters, and we got 0.1 meters per second, or in other words, 10 centimeters per second. Either of those are okay, as long as you know how to convert between the two. All right. What's an example of a transverse wave and a longitudinal wave? Describe how they're similar, describe how they're different. So both of these kinds of waves are oscillations that transfer energy or information. Waves on a string are transverse waves. Each segment of the string oscillates perpendicular to the forward motion of the wave. So that's our idea that we're shaking this string up and down, but the wave is moving left to right. On the other hand, sound is a longitudinal wave. The air molecules are moving back and forth, parallel to the direction of the wave's forward motion. So, and if you can remember from earlier animation, that the molecules themselves are just moving back and forth, but they're not actually moving with the wave. Okay, so finally, can you describe in your own words how a sound speaker moves to create sound waves? So I'll give you a moment. See if you can describe that with your with the person you're watching this with, and see if or if you're watching this alone, take a moment to try and reflect and write down, maybe draw yourself a picture. Okay, so a sound speaker moves back and forth to create waves. It oscillates and it creates these compression waves, which are longitudinal. And so in that way, in fact, we'll actually pull on a resource here. If you remember back to, let me go back to our activity, sound waves, and I'm going to use this one here. If we go to here, this is a nice little picture that kind of shows that there's a magnet in here, and there's some coil, and when there's electricity that goes to this coil here, it actually is pushing the cone back and forth, and that is causing subsequent compressions and rarefactions of the pressure. So that is a good reminder for you of how a speaker is creating sound, and if you understand that, and you understand how to calculate the frequency, wavelength, amplitude, and wave speed, then you're in good shape for understanding how to answer some of the homework questions and getting yourself prepared for our next exam.